flood is an overflow of water, or, in rare cases, other fluids, that covers normally dry ground. The word can also refer to the tide's inflow when used in the sense of flowing water. Floods are a topic of research in the hydrology field and are very important to the fields of agriculture, civil engineering, and public health. With regard to land use changes like deforestation and the removal of wetlands, changes in waterway courses or flood controls like levees, as well as larger environmental problems like climate change and sea level rise, human changes to the environment frequently result in an increase in the intensity and frequency of flooding. Particularly, the increased rainfall and extreme weather events brought on by climate change make other causes of flooding more severe, leading to more violent floods and a higher risk of flooding. Flooding can happen when water from water bodies, such as a river, lake, or ocean, overflows and destroys levees, allowing some of the water to escape its normal confines. It can also happen when rainwater collects on wet ground to cause an area flood. While seasonal variations in precipitation and snowmelt will affect the size of lakes and other bodies of water, these changes are unlikely to be significant unless they cause property to flood or domestic animals to drown. When a river's capacity is exceeded by its flow rate, particularly near bends or meanders in the waterway, floods can also happen. If they are located in the natural floodplains of rivers, homes and businesses are frequently damaged by floods. People have historically lived and worked by rivers because the ground is typically flat and productive, and because rivers offer easy transport, access to trade, and industry. However, riverine flood damage can be reduced by moving away from rivers and other bodies of water. In addition to causing physical damage, flooding can also have unintended consequences, including forcing long-term evictions of communities and accelerating the spread of mosquito and waterborne diseases. Floods can occur in flat or low-lying areas when snowmelt or rainfall deposit water more quickly than it can percolate through the ground or run off. The surplus builds up, sometimes to dangerous depths. Where the water table is shallow, such as a floodplain, or after intense rain from one or more storms, the surface soil can get saturated, which effectively blocks penetration. Additionally, infiltration through frozen ground, rock, concrete, paving, or roofing is slow to non-existent. Due to the fact that the velocity of overland flow depends on the surface slope, local depressions without access to a stream channel and flat places like floodplains are where aerial flooding first occurs. When precipitation surpasses evaporation, endorrheic basins may experience aerial flooding. Floods can happen in any river or stream channel, including the world's largest rivers as well as the smallest, ephemeral streams in humid regions and generally dry channels in desert climates. On tilled fields, overland flow can cause a muddy flood where sediments are gathered by runoff and transported as suspended matter or bedload. Drainage impediments like landslides, ice, debris, or beaver dams can either cause or make localized floods worse. Huge rivers with large catchment areas are where slow-rising floods most frequently occur. It's possible that prolonged rain, quick snowmelt, monsoons, or tropical cyclones are to blame for the rise in flow. However, since they may have enormous basins but limited river channels and rainfall can be highly strong in smaller portions of those basins, large rivers may experience quick flooding episodes in locations with a dry climate. Smaller rivers, rivers with steep valleys, rivers that flow a large portion of their length through impermeable terrain, or generally dry channels are more likely to experience rapid flooding occurrences, including flash floods. Localized convective precipitation, strong thunderstorms, or a sudden release from an upstream impoundment built as a result of a dam, landslide, or glacier could be the culprits. In one incident, a flash flood in a tight canyon killed 8 people who were having fun in the water on a Sunday afternoon. The flow rate surged from 50 to 1,500 cubic feet per second, 1.4 to 42 cubic meters per second, in just 1 minute, without any rainfall being seen. Within a week, there were 2 more significant floods at the same location, but nobody was at the waterfall on those days. A rainstorm over a section of the drainage basin, which frequently has steep, exposed rock slopes and thin soil that was already saturated, caused the fatal flood. The flow in downstream places is determined by the quantity, position, and time of water arriving in a drainage route from natural precipitation and managed or uncontrolled reservoir releases. Others precipitation evaporates, while others slowly percolate through the soil. Some may be momentarily trapped as snow or ice, and still others may quickly run off of surfaces like rock, pavement, rooftops, and saturated or frozen ground. From 0 for light rain on flat, dry land to as high as 170% for warm rain on compacted snow, it has been observed that the fraction of incident precipitation that rapidly reaches a drainage channel varies. The majority of precipitation data is based on the measured depth of water received during a predetermined period of time. The number of measurements that surpass an interest threshold for precipitation across the entire time period for which observations are available can be used to calculate the frequency of that threshold. The intensity of each individual data point is calculated by multiplying the recorded depth by the interval between observations. If the length of the rainfall event was less than the specified time interval for which measurements are recorded, this intensity will be lower than the actual peak intensity. Compared to orographic precipitation, convective precipitation events, thunderstorms, typically produce storm episodes of shorter duration. Forecasting flooding requires knowledge on the length, heaviness, and frequency of rainfall episodes. Flooding within tiny drainage basins is more significant after short-duration precipitation. The land area of the watershed upstream of the area of interest is the most crucial upslope component in determining flood amplitude. For watersheds smaller than roughly 30 square miles or 80 square kilometers, rainfall intensity is the second most crucial element. For bigger watersheds, the main channel slope is the second most crucial element. For small and large watersheds, respectively, channel slope and rainfall intensity move up to the third position in importance. The time it takes for runoff to travel from the farthest point in the upstream drainage area to the point where the drainage channel is limiting flooding in the area of interest is known as the time of concentration. The essential period of maximal rainfall for the area of interest is defined by the concentration time. For roof and parking lot drainage systems, the critical period of severe rainfall may just last a few minutes, whereas river basins would require a critical period of accumulated rainfall over a number of days. Eventually, downstream conditions encountered by water going downward slow mobility. The ocean or some coastal flooding bars that generate natural lakes are frequently the last line of defense for coastal flooding areas. Tidal variations and other elevation changes in low-lying areas are important factors of coastal and estuarine floods. Large bodies of water may experience elevation changes as a result of unpredictable occurrences like tsunamis and storm surges. The geometry of the flow channel, particularly its depth, flow rate, and sediment content, regulates the elevation of flowing water. Water elevation above flow channel constraints like bridges and canyons is frequently regulated. A closer point may control at lower water levels until a more distant point controls at higher water levels, as the actual control point for any given stretch of the drainage may alter with changing water elevation. The geometry of an effective flood channel can be altered by vegetation growth, ice or debris buildup, or the construction of levees, structures, or bridges inside the flood channel. Extreme floods frequently occur as a result of coincidences such as extremely heavy, warm rain that melts a lot of snow, floating ice that blocks the channels, and the release of tiny impoundments like beaver dams. Simplistic statistical prediction techniques that simply take into account precipitation runoff flowing inside clear drainage systems may underestimate the frequency of significant flooding due to coincidental events. Heavy floods that carry uprooted woody plants, flood-damaged structures and vehicles, including boats and railway equipment, frequently modify channel geometry with debris. Recent field measurements made during the Queensland floods in 2010 and 2011 demonstrated that any criterion that is exclusively focused on the flow velocity, water depth, or specific momentum cannot account for the dangers brought on by velocity and water depth changes. Further dangers connected with big debris entrained by the flow motion are disregarded by these calculations. The storage effect in cities with cut-and-filled traffic corridors has been brought up by certain scholars. If culverts get obstructed by debris, culvert fills may be transformed into impoundments and flow may be diverted along streets. The flow patterns and redistribution in roadways during storm events, as well as their effects on flood modeling, have been the subject of numerous research. That was for today. Thank you for staying with us. Don't forget to like our video and subscribe to our channel.